This is your friendly neighborhood physics teacher here, and we're going to talk about your spring final review. Okay, I've hinted at this a few times on our Zooms or in class, whichever one. But again, I would highly suggest you to know these vocabulary words. You never know, there might be a matching on the test. So, for momentum, if you see vector quantities, which is the product of an object's mass and velocity, that might be the definition for momentum. For static friction, if you see force opposing the motion of an object at rest, that might be the definition of static friction. Impulse, product of a force and the time over which it acts, might be the definition for impulse. Kinetic friction, force opposing the motion of an object. Mechanical energy, sum of the kinetic and potential energy within a system. Field forces, occurs between two objects when let's try that again. Occurs between two objects even in the absence of physical contact. An example of that is gravity. Inertia, tendency of an object to maintain its state of motion. Weight, magnitude of the force of gravity acting upon an object. A normal force, exerted by one object on another perpendicular to the surface of contact. Acceleration, a change of velocity which occurs over some change in time. Velocity, a change in displacement which occurs over some change in time. Equilibrium, state in which there is no change in a body's object or moving at constant velocity. Angular acceleration, rate of change of angular speed. Angular speed, rate at which a body rotates around an axis. Angular displacement, angle through which a body rotates in a specific direction about a specific axis. Centripetal acceleration, acceleration directed towards the center of a circular path. Tangential acceleration, instantaneous linear acceleration of an object directed along the tangent of the object's circular path. Tangential speed, instantaneous linear speed of an object directed along the tangent of the object's circular path. Torque, quantity that measures the ability of the force to rotate an object around some axis. Center of mass, point at which all the mass of a body can be considered to be concentrated. Rotational motion, motion of a body that spins about an axis. There we go. I know we still have a few to go over. I still need So let's continue on, shall we? So those are your vocabulary words. I think there's a few more on the list, but we will touch on those when we get there. So a couple of other things that you might, maybe, potentially, could be tested on is which of the following has the greatest momentum? And I'll give you different objects. So that's knowing the equation. So remember, your equation for momentum is P equals mass times velocity. So to have a greater momentum, you either need to have more mass or more velocity. You sit there and just take your mass, take your velocity, multiply it together, and see which number comes out the biggest. And that's how you'd find out object has the greatest momentum. Your SI unit for mass. So hopefully you remember that your for mass, it's kilograms. An object with a mass of some big number in grams would have a weight of blank. So let's say, so this is where knowing our equation of force of gravity comes into play. That is momentum. Force of gravity, or weight, is force of gravity equals mass times acceleration due to gravity. So you would multiply them together, but you would need to convert that grams to kilograms. So to convert from grams to kilograms, there is 1,000 grams in 1 kilogram. So that's when you do your lovely little railroad track. So you would go from grams. We don't want grams, we want kilograms. So you'd end up doing 1,000 over 1, whatever number, and then divide. So that's how you would convert. So again, if you have a net force of something causing an object to accelerate, we see centimeters per second squared. Do we like centimeters? So is our SI unit, what is our SI unit for distance? Hopefully you said meters. So again, we would need to convert. This is where the definition of force comes into play. So definition of force equals mass times acceleration. So again, you would just multiply, well, in this case, we're looking for mass. So, nope, we're looking for mass. We want to get mass by itself. So we would end up getting mass equals force divided by our acceleration. You would just take your force divided by the acceleration. But our acceleration is in centimeters per second. We don't want centimeters. So centimeters get shunned. We want meters. And there are 100 centimeters in 1 meter. 100 centimeters equals 1 meter. So you would need to do a little bit of conversions before you multiply. So we have an object with a certain mass, it's moving at a certain speed. Oh, hopefully it looks like we're going back to our momentum equation over here. It says, then that object is hit by another object, rebounds in the opposite direction, and we have a new speed. What is the change momentum? So to do our change momentum, so we're still going with momentum, but our change momentum equals our mass times change velocity. So the mass of the object is not going to change, so it just stays. But remember, our change velocity is our final velocity minus our initial velocity. And if it's a rebound, that means it's going in the opposite direction. So that number will be negative. So in this case, you would have a negative final velocity, but you would still do a minus your initial velocity, which would be in the positive direction. That'll make a little bit more sense there. So there we go. So you would need to do that, then multiply your number by the mass. So again, it's looking like a momentum equation, or a momentum question here. We have two objects that are moving. Oh, so this is where we get into collisions. So it will either be an elastic collision or an inelastic collision, according if they stick together or not. Okay, so we have a one object that's moving on a frictionless surface, and it has a mass and it has a velocity. We have another object that's again moving on the frictionless surface, has a mass and a velocity, but they're coming at each other. And it's just asking, so this was just asking what is the total momentum of the two system. So again, we're going into momentum here. So we're going to go over here. So it's still momentum. So anyway, to do total momentum, it's just momentum of your first thing plus momentum of your second thing. And direction does matter. So it'd be the mass of your first object times the velocity of your first object plus, but direction does matter. So let's say your second object is going in the negative direction. That means your velocity of your second object is going to be negative, and you do have to take into that consideration. So remember, left is negative, right is positive. And then you just add them up to get your total momentum of the system. So this wasn't quite, it's colliding, but we just did first part, not the one second part. Okay. So now think about, you have a very breakable object and it hits a hard surface versus the breakable object hitting a softer surface. Why does the object survive the softer surface versus the harder surface? Again, we're talking about momentum here. And actually, we're not necessarily talking about momentum, we're jumping to impulse here. So we're going to jump to impulse. We're going to do all the way over here. So remember, impulse is force times time, technically, your change in time. And so going from harder surface to softer surface, basically what you're doing because we want, our ultimate goal is to decrease this force. So to decrease that force, we have to increase the time. Because if you think about it, remember impulse, let me stick with this book. Remember, impulse is equal to your change of momentum. And no matter the same an object hitting a hard surface versus that same object hitting like a soft surface is going to have the same change momentum. As you remember, change momentum is just mass times change velocity. The mass doesn't change, and the change of velocity doesn't change. It'll be falling at whatever rate it's falling, then going to zero. So this stays the same. So if this is the same, then this is the same, and so forth, this is the same. So the only two things you can kind of change would be equivalent to be the time and the force. So we don't want it to break, so we want the force to decrease. So that means we need to increase the time. And so the softer thing would increase the time because it slows it down. So it's not abrupt, not abrupt stop. It's just so you're increasing that time to decrease the force. Okay, so we're going back to momentum here. So we have an object running in a straight line. If we so we're looking at our momentum equation. So if we double the mass, we're doubling the mass, and then we're halving the speed. How will that affect the momentum? The only thing the only thing that's different is 2 over 2 is still mass times velocity. What's 2 over 2? It gives you 1. So it really doesn't change it at all. So there's no change. So it'd just be a factor of 1. Okay. So if you have two objects that collide and stick together, what type of collision is that? So this is where we're getting into our collisions. So inelastic, big thing about inelastic is a loss of energy, specifically kinetic energy, and sometimes they stick together. Not always, but if it sticks together, it is definitely an inelastic collision. Come back. There we go. Our elastic collisions is everything is conserved. Everything's conserved. Energy, momentum. So if it sticks together, it's definitely going to be an inelastic collision. Again, what is the factors of momentum? We just go back to our equation, so it'd be mass, it'd be velocity. Now, I know a lot of people want to say time and force also. This specifically says momentum, not change in momentum. Remember, force and time are just change in momentum. The only two factors that really affect just momentum is mass and velocity. So now we're going to be talking about our torque. So our torque equation, is force times radius. And remember, radius is how far the radius from the axis, so its point of rotation. So if we have a door here and the hinges are on this side, it's going to rotate this way and this way, right? So if we have the doorknob here, our radius would be from here all the way to there, to the hinge. That would be our radius. Now, again, torque is the same so our torque is going to stay constant. So if we're dealing with the same door, no matter where we push it from, torque is going to stay the same. What's going to change is our radius and our force. When we go to open up something, again, we want a very low force, so that means we need a high radius. So think about that. So we want the doorknob to be on the end to be the radius. But if our doorknob is in the middle, we're going to end up cutting our radius in half. So that's going to change the whole entire system. And again, to find torque, it's just force times our radius. Force is in newtons, radius is in meters because it's a distance. So again, the further you are out from the point of rotation, the easier it is to open. That's why when you start doing, like, if you do anything in the car, you have like our wrench, you have those really, really long wrenches, so you don't have to put as much force into it. So again, this, knowing your definition of torque. So basically, again, it's the ability of a force to rotate or accelerate an object. Definitely know the definition of torque. Your universal gravitational law, I would know that too. So we're going to go, we're going to go down here. So our universal gravitational law is our universal gravitational constant times mass 1 times mass 2 over r squared. Please don't forget about the squared. Remember, your constant is 6.673 times 10 to the negative 11. So that is your constant. You would plug that in there. If you have a graphing calculator, you can plug it in with your big E. It would just be negative 11. You can do it like that. Also, if you're going to use the caret, make sure you put parentheses around that. And basically, you would just do mass 1, mass 2 divided by your r squared. Plug it in. The best thing is to put parentheses around everything so you don't mess up your calculations. So again, just your torque, going back to torque, just force times radius. Ooh, okay. So now we're going to get into, so we're doing it on an incline. So we're doing this one. So we have an incline here, and we have a box. So let's see here. So our force of gravity, go straight down. Our force of normal goes perpendicular with the surface. And then since the box wants to slide down because of gravity, our force of friction always goes opposite of the motion. So that's kind of what our free body diagram would end up looking like. On a flat surface, so we're there on a flat surface. Again, oops, force of gravity would be going down. Force of normal would be going up. And if there is movement, force of friction would be going in any of the opposite direction of the motion. Let's say we are swinging, so we have a ball on a string. It's going around in circles. This a little bit better. Okay, it's going around in circles. And all of a sudden, when the ball gets down here, so it's moving this way, and the ball gets down here, and the rope breaks. Which direction is this ball going to go? Hopefully you said straight, because it's going to go with its tangential velocity. It's going to go with its tangential velocity. The thing that was keeping it going in a circle was the tension, the force of tension. Your force of tension was your centripetal force. Without that force of tension, it's not going to go in a circle anymore. It's going to go where inertia wants it to go. An object motion stays in motion. At that split second, the motion was to the right. So guess what? It's going to continue to the right. Now, eventually, gravity will be like, oh, it's free. I want it, and start pulling it down. But for that split second, right when it gets cut, it's going to be moving to the right. So just to the right. So we would ignore this. Okay. Hopefully that helps you with your review. If you have any questions, please don't hesitate to ask Miss Templeton. She loves to help, I promise. I kind of personally know her. Hope you have a wonderful day. Happy studying for your finals. Good luck. I believe in y'all. You're almost done. We can do this. Remember, you're loved and appreciated. Bye.